Good afternoon. Thank you for joining. I'll start the class shortly. And meanwhile, please let me know if you can see my screen.
Yes, ma'am.
Thank you, sir.
Ashti, ma'am.
Yes.
Ma'am, in last assignment, one program is given which is very complicated. That means the calculation is very lengthy. So,
Okay.
can such type of program come in the exam?
I don't think so. If the this is just for your practice and just to give you an idea how to solve and how you should get the answers. But since the exam will be very time, there will be time limit. I don't think very lengthy
Yes.
calculations will be given in the exam.
Okay, ma'am. Because we know the concept but unable to solve the problem.
Yeah. Actually, see, for these assignments, you get like 1-2 weeks to solve your problem. So the length doesn't matter there. But when the time is
Yes, yes.
short, then the problems will be given accordingly. That is, I believe so. I am not setting the question paper, so I don't know
Okay.
for sure.
Yeah. Understand.
So, but I believe it will
Thank you.
not be that lengthy.
Okay.
Okay. Any specific doubt from all the lectures and all my clearance these problem solving sessions? If you have anything, please feel free to ask.
No, ma'am. Actually, problem solving session, we have no any doubt.
Okay.
We solve all the assignment according to your lecture.
Okay.
Because you are unable to attend the lecture class now. So because this is 1 hour class, we spend 1 hour, but lecture class is the 2 and 3, 3 and 4 hours. That,
Okay. It's
but we
fine.
can understand all the programs of the solution class.
Okay. So I'll start now. I don't think anybody else is going to join on. I'll start
Yes,
it.
ma'am.
So this is about so as I understand, you haven't gone through week 12 lectures, I suppose.
Yes, ma'am. Yes.
Okay, fine. So, what was done in week 12 was we were introduced to a concept of generalized least squares. So, very briefly, we had done uh, we had previously we had fitted generalized least square where the variance of epsilon, this just note this term, generalized least square, that is GLS. This was done when the variances were not constant. So we did this with the weighted there was a weighted technique and the GLS technique where we took the variance covariance matrix into consideration. Somehow we implemented this matrix into the regular least square estimate of beta hat and we got the GLS estimates. So that was generalized least squares. Okay, so what we were introduced to in this week was generalized, I'll write it down. So this week what we learned was not generalized least squares, we were generalized linear models or very frequently known as GLM. Okay, so how is that different from generalized least squares is that for this model fitting, the GLM model, we assume that the error terms are not normally distributed. So here the error is normally distributed but the variances are not constant. But for
Sorry, ma'am.
yes.
Error term is normally distributed in this case.
So for generalized least squares, when we did in the previous classes, where you remember we had done beta hat equal to x transpose v inverse x, x transpose y.
Yes, ma'am.
So this was
yes.
the GLS estimate. Sorry, I
Okay.
wrote it wrong. 1 second. There should be a v inverse here.
By
Yeah.
inverse.
V inverse y. So this was
Y.
the generalized least square. So here the assumption was the variance covariance matrix, this was not equal to the identity matrix. So when this variance covariance is not equal to the identity matrix is what? Sigma square into I means all the diagonal elements are the variances of y and those are constant, and the off diagonals are 0, that means the errors are independent. So we did this, we assume that this follows something like this. Okay, the epsilons. This was the generalized least square model, but now we are looking at generalized linear models. So this was actually a technique, and here the model itself is changing because we are assuming, like here we say yi equal to x beta plus epsilon, we had it. So this one is not normal. So we can no longer assume that it follows a normal distribution. When such a scenario occurs, then we fit generalized linear models or GLMs, which are different from the OLS or ordinary least squares, which assume that the errors are normally distributed. Okay, so this entire thing was introduced. The basic concept is that the errors or the response variable, they are not normally distributed. But in order to fit a generalized linear model, these response variables should have some distribution which must belong to the exponential family of distributions. So I'll tell you, this exponential family, there is a certain characteristics, okay, which are very suitable. So for fitting generalized linear models, one should ensure that the error distribution or accordingly the response variable distribution belongs to the exponential family of distribution. Now why I am saying error or response, because you see we are assuming that the x part is not, the x or the regressors are not random, they are non-stochastic. So that is why what will be, in most cases, whatever will be the distribution of the error, the distribution of y will also be the same, because this is not a random term. Okay, so distribution of y and distribution of errors will have to belong to the exponential family of distribution so that we can fit a generalized least squares. So how do we do it? Instead of fitting y equal to x beta plus epsilon, we fit some g mu equal to x beta plus epsilon, where mu is the expected value of y. So this is the general concept. We have to find a suitable link function to transform our to fit the mean of our response. Here in ordinary least squares, what we do, we try to account for variation in y, how much of variation is y is captured by variation in x. But in generalized least square, we do how much of variation in the mean some function of the mean of y is being explained by the regressors. Okay, so this was what was explained here, and as I was saying, you have to first check whether the distributions belong to the exponential family of distributions. So there are one parameter, two parameter exponential family of distributions, but we did not go into much of detail. So how will we characterize that whether a distribution is belonging to the exponential family or not? So if let's say we have the probability mass function, this is the probability mass function, or the PDF, that is the probability density function. So if we know this, if we know y follows some other some distribution, so if we know what distribution it follows, or if we can make a guess about what the distribution is, then we have to test whether that distribution is following the exponential family or not. And if it is an exponential family, then the PDF or PMF, I am writing it as y theta. Theta is the unknown parameter of interest. For example, if let's say if we have a Bernoulli trial, okay, let's say head turns up with probability p and tail turns up with probability 1 minus p. So p here is the term of interest, unknown parameter of interest. So that is being characterized by the theta term over here. So the PMF or PDF, if it can be expressed in this format, e to the power of a y b theta plus c theta plus dy. If the PDF can be expressed in this format, then we say that y is from an exponential family of distributions. Okay, so we'll have some functional form which will have both the y, both the random variable and the parameter of interest. They'll come together. Along with it, there'll be some other terms which will solely contain the variable, the random variable, and solely contain the parameter. So if the PDF or the PMF probability distribution, if the distribution can be expressed in this format, then we say that this is from an exponential family of distributions. And very specifically, if ay is y, if this is the identity function, instead of ay we have just y, then we say that it is in its canonical form. Okay, and this parameter which is associated with ay, this b theta, this is known as the natural parameter. So these are a few terms which will be of importance. So this natural parameter is most often the link function g. Okay, so whatever will be here will fit. Let's say the b theta equals to some x square or theta square, let's say, then we'll fit g of mu equal to x beta plus epsilon, which will be mu square equal to x beta plus epsilon, something like this. Okay, this is just an example. So this whatever.
Ma'am, theta is the natural parameter.
Theta is
Natural parameter.
No, b theta is the natural parameter, not theta.
Okay.
This function, this entire function.
Entire function.
Yes, this entire function is the natural parameter, which will most often define what the link function will be. So as I'm saying, if you have, let's say, b theta is theta square, as I mentioned here, then theta square is the natural parameter. and we would fit this thing g mu instead of g mu we would write mu square equal to x beta plus x beta
Yes,
plus
ma'am.
epsilon. Okay.
Yes, ma'am.
We would fit, yes, g x beta plus epsilon. So we'll do sums to check how whether what family belongs to this category of distributions. We'll do it today, but before that, if we are to, so here, like I said, this f of y theta can be written as e to the power, just remember this is e to the power, okay, e to the power this thing. So e to the power ay b theta plus c theta plus dy. So if we are to find out the mean of ay, it is given by c prime theta by b prime theta, and variance of ay is given by b double prime theta c prime theta minus c prime theta b prime theta by b prime theta whole cube. Okay, so what is the usefulness of knowing this formula is that if you are given a distribution which is not very known to you, but it falls in the category of exponential family of distributions, and if you find, if you are to get the expected value of this function, then you can readily find it out. Also, if it is in canonical form, then ay will be y, then directly from here you can find out the expectation of y and variance of y. If you don't know what I mean, the PDF, I mean, obviously you will know the PDF, but if it is too much of calculation involved there, and if this is easier, I mean, this is just another way. That is what I'm trying to convey here. Okay, sir?
Ma'am, double derivative, be double derivative.
This is double derivative, yes. So as I was saying in this thing, let's say you have your parameter involves p, so here this will be with respect to that unknown parameter, derivative with respect to that parameter. Okay?
Yes.
Can I proceed?
Yes,
Okay.
ma'am.
Okay, sir. So first thing is done. How we are checking? So the first checkpoint was the errors are not normal, and then we are checking y follows if whether it is from an exponential family. If it is in the exponential family, we get the link function, which is b theta, and then we proceed to fit the GLM model. So like I said, the choice of link function here is b theta. Okay, and so you must have heard of some other forms of regression where it is logistic regression or Poisson regression. So what happens is that in case of a logistic regression, the y variable is a binary variable, a yes no type of variable. Okay, so and you see some regressors over here. For example, let's say if let's say whether you will buy a car or not. Okay, so it's either a yes or a no situation. So it might depend on various things, your income, then the inflation and cost of living, so many factors. So you see, your x beta plus epsilon, this I'll leave out x epsilon for the time being. So this x beta with x1 beta 1, let's say this one corresponds to your income, okay, plus x2 beta 2 plus something plus xp bp. Let's say this is some other your utility that you are going to derive from your car. So these things, these values may range from minus infinity to plus infinity, but your y variable will just be a 1 or a 0 thing, correct? So in such cases, what we do, we usually fit the ln of p by 1 minus p equal to x prime beta, and we call it the logistic regression. So what happens, p by 1 by p, this is a proportion, and this ln value, if we p is between 0 to 1, okay, so this value can be between this entire thing can range from minus infinity to infinity now. So the right hand side can also range from minus infinity to infinity. The left hand side can also be from minus infinity to infinity. So instead of fitting y equal to x beta, which doesn't which doesn't make much sense, we fit a logistic regression where this is nothing but the unknown parameter of interest. Now how do we derive this, what this ln p by 1 minus p is actually the logit link or the link function. So this is derived from, since this is a binary variable, this follows a Bernoulli distribution 1p, let's say, and then we write down the distribution in that exponential family form, and we find that b theta will be something ln p by 1 minus p, okay, that we use, and we fit it. So using this model, we carry out some iterative techniques, which is not discussed in details over here, and then solving this one, we would get values of beta hat. Similarly, for a Poisson regression, we have a log link, okay, so we would have ln mu equal to x prime beta plus epsilon. So when do we use a Poisson thing? Poisson distribution we use normally for counts, like number of accidents in 1 year, or number of mistakes in a book, let's say. So in those situations, we use this link, and then we try to find out beta hat, and we do it by, there are various techniques, mostly we use maximum likelihood estimation, and then we get the values of beta hat by some iterative techniques. But the procedure is this one. We see whether if it is normally distributed, if it belongs to the exponential family, we get the link function, then we write it down, we write down the likelihood of y, and then we solve iteratively for the parameters of interest and get the parameter values, okay. So as I was saying, so what will be the maximum likelihood estimation method? So let me first start with the logistic one. So as I was saying, y follows a Bernoulli p distribution, or equivalently binomial 1p, okay. It can take either 0 or 1 with probability p and 1 minus p, let's say, okay. So this thing we can, so f of y can be written as p to the power y 1 minus p to the power y in such cases, because when y is 0 we have 1 minus p probability, and when y is 1 we have, when y is 0 we have something I wrote, 1 minus y, yes. p to the power 1 minus y. So here from you see if y equal to 0, then this term remains, 1 minus p remains. That is the probability. And when y is 1, then this term remains, then the probability is p. Okay, so this is the PDF of y. Now if you have, since we are talking about estimation, estimation is mostly based on a sample of n observations. So, and we are taking random sample, which means that observations are independent. Okay, so when the observations are independent, then f of y1, y2, yn, we can write it down as product of f of yi, since these are independent and identical IID. So if we write this thing here, what we'll get is product of p to the power yi 1 minus p to the power 1 minus yi. So if we write it in terms of exponential form, then we can write it as exponential of log of this thing, product of pyi 1 minus p 1 minus yi. Okay, so if we solve this, then this will become ln, one second, this will become summation, the product term will become summation. We would have yi ln p plus summation 1 minus yi ln, this will be pi, I am sorry. Okay, and then we can write it as summation yi ln pi by 1 minus pi plus summation ln pi. Okay, so from here you see we get that link thing, and since we know this is the link function, I'll give a new slide. So what we derive from here is that fy equals to exponential summation yi ln pi by 1 minus pi plus summation ln 1 minus pi. And we know this, we are fitting this thing, right, for a logistic regression. So instead of these terms, we'll use this one, we'll substitute. So we'll have yi xi transpose beta plus summation, this thing, if you write carefully from here only, this we'll just then from here pi by 1 minus pi will be e to the power xi transpose beta, and if we just shift it, then 1 minus beta will be this thing, 1 plus e to the power xi transpose beta. So now we got our fy. So this is the likelihood function. So what we do, we'll differentiate this function with respect to the parameters of interest, and then we would this is the likelihood function. So in order to simplify, we'll take the log likelihood. Then ln of fy would be nothing but this term over here, and this one we would differentiate with respect to beta, and then we'll carry out this differentiation iteratively. There are various techniques to ultimately arrive at beta hat. Okay, so this is how we are fitting a nonlinear model. Is it a clear, a little bit, or any other doubt?
Yes, I'm little bit clear.
Little bit clear. I know this is a very complicated procedure. So what I need you to remember is that you get the link function. For the exam purpose, I don't think this fitting will not be given. So you get the link function. The procedure is to jot down the likelihood, get the log likelihood, because differentiating likelihood and log likelihood is the same thing. Then we differentiate with respect to parameter, and this is the maximum likelihood. So this is like maximum minima. We differentiate, and wherever the second derivative is greater than 0, that point is the maximum. So in similar concepts, we differentiate with respect to the parameter, and then we do it, and there is an iterative process which we carry on until and unless this beta hat value converges to some estimate. Okay, so this is the entire crux of fitting a GLM. And so much of details has not been said in class, but please remember, this is how you should proceed. Similarly, I'll do one more for Poisson. For a Poisson distribution, we can write the likelihood. First, let's say yi follows Poisson lambda I. Okay, so this thing we can write it as product of e to the power minus lambda I to the power yi by yi prime I equal to 1 to n, and then we take the log likelihood, log of f of y1. This we'll have it like summation e to the power minus xi prime, sorry, this one we would have as minus lambda I plus yi log lambda I minus log of yi factorial, the entire thing. Okay, and then since we have in Poisson we have a log link, that is we would fit this thing. So instead of wherever we find log lambda I, we'll substitute by these beta values, and this lambda will also be e to the power minus this thing. And similarly, by substituting these values with the x's and the betas, and then differentiating with respect to the betas equating to 0 and solving iteratively, we would arrive at the GLM estimates. Okay, is this the procedure a little clear? Okay, so don't worry, so much of details will not be needed. Just remember how we should do fitting. So then we would it was discussed something about linearity and non-linearity. So we are studying linear models. So this linearity is with respect to parameters. This is a very important concept that we should remember, because we have fitted polynomial regressions like, right, it's x plus beta 1 x square plus beta 2 x square. This is also a linear model. The regressors might have some power attached to it, but the parameters beta 1, beta 2, beta 3, these are linear. Okay, so we also talked about something like y equal to e to the power beta naught plus beta 1 x1. So even though this is non-linear, but the log transformation will make it a linear in parameters beta naught and beta 1. So whenever we encountered such models, we did a log transformation, and then we fitted on the transformed y, we fit the regression, and then we used to get beta naught and beta 1 hat. So linearity is always with respect to the parameters and not the regressors that are involved in the model. Okay, if we have something like y equal to beta naught plus e to the power beta uh, 1 by 1 minus e to the power beta 2 x1, then this is, even though this one doesn't have any power associated with this term is non-linear. So the model then becomes a non-linear model. So in case of a non-linear model, the techniques were discussed. If you did not have time to go through the lectures, this is the last lecture. If you want, you can go through the lectures, or you can see the lecture notes, because this is a little bit detailed in terms of derivations, and I really want to solve the problems which are necessary for this course and the exam. So please go through that lecture if you have it. Okay, it's there, it's put up on the website. So you go through the theoretical lectures. Here also there is some approximation with respect to we are, so the model is fy will be some function of the regressors. There are different notations that have been used, and some parameters also, and then we would have to, y would be some, instead of x beta, it will be some function of x and the regressors theta plus epsilon, and a detailed derivation is given in the lecture notes. So you please go through that. Okay, I will I'll not because I'm running late. This one, if I say, it will get too late and I won't be able to solve the problems. So I would urge you to look at the lecture notes. There it is given how the normal equations in a nonlinear setup are derived. So very briefly I'll tell you, in a nonlinear setup y will be some function of this x and theta. Okay, some different notation has been used. I'll use that. The t here for nonlinear case, the t is the regressors. Okay, and you, instead of indexing the samples by I, they have indexed it by u. So plus epsilon. So this will be the model, and the concept is same. We get the residual sum of squares, that is yu minus f tu theta square summation over u. Okay, so this will be the residual sum of squares in terms of theta, and we would differentiate with respect to theta this quantity yu minus f tu theta whole square, and we would equate it to 0. Now this one would be, this 2 would come down, summation 2 yu minus f of tu theta, and then we would again differentiate in terms of this is the chain rule of differentiation. So we'll again differentiate this term f of tu theta, and then we would equate it to 0. Now the important thing to note is that here, since the model is not linear in theta, there will be terms involving theta. Okay, in a linear model, this part we did not have to bother about, because the parameters were always single, and whatever was with that came here. So this part was totally independent of the parameter of interest. But now that is not the case. This part will also involve theta, and this solving the equations becomes much more challenging in such scenarios. So some sort of approximation is done where this f tu theta is there's a Taylor series transformation, and then iteratively we arrive at theta. Okay, that's a very detailed and a little difficult to understand, but if you go through the lecture notes, you will get an idea of it. So this is why we need to do things in a nonlinear setup differently, because this term, when we are writing the residual sum of squares and then following the chain rule, this term is not independent of theta. It will involve a theta term. Okay, and so like I said, it's an iterative procedure and which is detailed in lecture notes. So with this priming, I will solve the questions that are there corresponding to this week lecture. So sir, are you there?
Yes, ma'am.
Okay, okay. So let me just start with the questions. So here you see we have n observations on the regressors, and y is a response variable where y's are binomial ratios. Okay, so we know that y ri is the number of successes in m terms, let's say. Okay, ri follows binomial m and it's something p, let's say. Then ri by m, this will follow binomial 1p. This is the proportion. So here whatever it is, since it is given that this is binomial ratios, so even if this concept is not known, since it is given that they are binomial ratios, we would like to get a reasonable choice of y. Okay, so m is a constant and ri is the number of successes. This will follow Bernoulli p, okay, or binomial 1p. So whatever it is, so what we'll do, we'll just write down fy. So fy would be p to the power y 1 minus p to the power 1 minus y. So this one we will write as e to the power log of p to the power y 1 minus p to the power 1 minus y. This one we can write as ln p to the power y plus ln 1 minus p to the power 1 minus y. So here then this thing will come in the beginning. We can write y ln p plus 1 minus y ln 1 minus p. So again here this will be y ln p minus y ln 1 minus p plus ln 1 minus p. So this is nothing but y. So if we take y common from here, this will be ln p by 1 minus p plus ln of 1 minus p. Okay, so if you match it with this form, ay b theta plus c theta plus dy e to the power, then you see that here ay is nothing but y and b theta is ln p by 1 minus p and c theta is ln 1 minus p. dy is nothing here, 0 in this case. So the reasonable choice of fy, so whatever I was telling in terms of g equal to x beta plus epsilon, so that g is only written as f here. So then the reasonable choice would be this one, ln y by 1 minus y. Is it okay?
Ma'am, you are taking exponential for transforming the conical form.
No, no, no.
Okay.
I am taking exponential to match it with the OPEF form. Sorry, to match it with the exponential family of distribution form. Because here the characterization says that it should be e to the power this form, ay b theta cy dy. So whatever is this thing, I'll first try to write it in an e to the power format, e to the power log, and then this part I'll try to tease out the individual factors in terms of y and the parameter of interest. So here the parameter of interest is my p. Okay, so I'll see if y and p terms can be, if they come together, I'll try to get them together in one term. I'll try to get something solely in p and something solely in y. Now if it is not possible to do that, then we say that it doesn't belong to the exponential family of distribution. But to match this characterization, I am taking exponential.
Okay. Okay.
Okay, so I'll solve a couple of more
So
problems. Yes, yes, say.
means the exponential family of distribution means binomial and normal. This is the exponential family, no?
Yes, binomial, normal, Poisson. These are the normal exponential distribution. These follow from the exponential family of distributions.
Okay. In this case, first we transform in the exponential form, then we compare.
Yeah, we have to compare, because this characterization says that it can be written in terms of e to the power ay b theta. So just to match
Okay.
it with that, I'm doing this. Okay. So
Okay.
similarly here also we have another density function, 1 minus p x minus 1 p. So is this density a member of the exponential family? So same thing, f of xp is 1 minus p to the power x minus 1 into p. This one we'll write at e to the power log n of 1 minus p x minus 1 p. So again this is ln 1 minus p to the power x minus 1 plus ln p. So this is exponential x minus 1 ln 1 minus p plus ln p. So then this one becomes the b theta. This is ax and this is c theta. Again dx is 0 over here. So since it can be written in this format, we say that yes, it belongs to the exponential family. Okay.
Yes, a missing term, that is the dx.
Dx is missing. Dx is a function of x. No, it doesn't involve the parameter. So here it is 0. But it might not be
Okay.
0 in all cases. Okay. So here is another one. Is this in its canonical form? So first we see if it is in the exponential form or not. So this one we'll write, this one is theta minus 1 plus theta. So this is theta 1, okay, like this only we'll write. So e to the power log of theta x minus 1 plus theta. Okay, so this will be e to the power ln theta plus ln x to the power minus 1 plus theta. So this thing will be ln theta minus 1 plus theta ln x. So this one is c theta, this one is b theta, this one is ax, and again dx is 0 over here. So this one belongs to the family of exponential distributions. But you see ax equal to ln x and not equal to x. So is this in its canonical form? The answer is no. Okay. again similar. This is a Poisson variable. So for Poisson, what is the PDF? F of y equals to e to the power minus lambda, lambda to the power y by y factorial. This one we'll write as exponential log e to the power minus lambda, lambda to the power y by y factorial. Here exponential ln e to the power minus lambda plus ln lambda to the power y minus ln y factorial. So this can be written as minus lambda plus y ln lambda minus ln y factorial. So for this case, you see ay is y, b lambda is ln lambda, this term ay and lambda together. This is solely lambda, that is c lambda is minus lambda, and dy is minus ln y prime. It's not 0 in this case. Okay, so the reasonable choice is whatever is with this ay, that is b lambda, which is log lambda in this case. So the answer is A. Okay. So again we have the other one. Here they are saying this is a negative binomial probability mass function. So this one also we will try to write as exponential log of this entire thing, x plus r minus 1 cx p to the power r 1 minus p to the power x, which is equal to exponential ln log multiply can be written as separately x plus r minus 1 cx plus r log p plus x log 1 minus p. Okay, so here note this is a function in x and p only. R is not this is not of interest, and somewhat it is known. Okay, or known, not of interest or not known. So this is a function in x and p only. So then this term we'll not bother much about. So if we look carefully, this one is nothing but ax into bp. This one is cp and this one is dx. So the natural parameter in this case is, this is the natural parameter. So bp is ln 1 minus p. That is the answer. Okay, sir? Okay. Similarly, if we are not given the PDF, then we have to remember what are the PDFs of these variables. Okay, so suppose it is said that it follows a gamma distribution. So then the gamma PDF is written as theta to the power alpha by gamma alpha y to the power alpha minus 1 e to the power minus theta y, where theta alpha are both greater than 0 and y is greater than equal to 0. Okay, and here the parameter of interest is this thing theta. Okay, so similarly we'll write it as e to the power ln this entire thing y to the power alpha minus 1 e to the power minus theta y e to the power ln theta to the power alpha minus ln gamma alpha plus alpha minus 1 ln y minus theta y. So this is e to the power alpha ln theta minus ln gamma alpha plus alpha minus 1 ln y minus theta y. So here you see this is b theta ay, this term. Okay, this one, since alpha is not my parameter of interest, this one is my dy, and this thing we can consider it as c theta, or we can consider c theta this part and club this one and this one together. This part is flexible. So the reasonable choice of fy in this case is y. Okay, ay equal to y. Now what I want you to emphasize here is that instead of in case of exponential distributions, it really depends on how you are characterizing the equation. For example, let's say x follows an exponential distribution. We can exponential theta, then fx is theta e to the power minus theta x for x greater than 0. But if x follows an exponential with mean 1 minus theta, then fx would be 1 by theta e to the power 1 minus x by theta. So depending on the form of the PDF that you are taking, the canonical or the natural parameter will be different. Natural parameter will differ. Okay, because in this case the natural parameter, if you derive, you will see it will come as 1 by theta, but in this case the natural parameter will be theta. So both are exponential distributions. So for exponentials and gammas, I would urge not to blindly follow a flowchart, but actually write down the PDF and then find out the natural parameter. Okay, this is something that I wanted to make very clear. So similar type of problems here. We have a Weibull distribution. This is how a Weibull distribution looks, and then here,
ma'am,
yes,
nature parameter depend upon the response variable.
natural parameter doesn't, well, of course it will depend on the distribution of the response variable, but it will also depend on how you are writing the PDF. Okay, so for here
Most of the case PDF is the given now.
PDF is given, but suppose if it is if there's ambiguity, let's say, I mean if it is given that it follows an exponential distribution, and then this is the form of the distribution. Okay, and they are asking to find out the natural parameter. So if you write the equation and solve it, then you will get it, you will not have any problem. But there is a table in the lecture notes which says that for exponential, the the natural parameter is 1 by y always, but it's not so. It depends on how you are characterizing this thing. So I'll try.
Because sometimes very confusing. How can understand which is natural parameters or which one is not?
So in such cases, uh, it will be given. From what I believe, see, this exponential distribution has a mean of 1 by theta, but this exponential distribution has a mean of theta.
Yes, yes.
So that is what I'm saying. Suppose you forget the form sometimes, or by seeing sometimes it happens, no, you see exponential in the first line, you don't look at the PDF and just directly you give 1 by y as tick. So I'm what I'm trying to say is, that you should abstain from doing this. Instead, you should write down from the PDF and then solve it. Because there are some people, I'm saying this because when you're running short of time, you tend to overlook things. So I'm just urging you not to do that. If your PDF is given, you write it down properly and then arrive at the proper natural parameter.
Okay.
Okay.
Yes.
Because in the during the lectures and in if you Google also, sometimes they'll give you that for exponential this is the natural parameter, but what they often fail to discuss is what form of the PDF are they taking into consideration to derive this natural parameter. So I'm just trying to I'm just urging you to exercise a little bit of caution and judge accordingly. If a PDF is given, you write it down in that format and then arrive at the answer. So here again, this PDF, what we have, fx, and the k is a nuisance parameter. We are not interested in k, so we are interested in lambda. So we'll write it as fx lambda k by lambda x by lambda to the power k minus 1 e to the power minus x by lambda to the power k. Okay, and then similarly log of k by lambda plus log of x by lambda to the power k minus 1 minus x by lambda to the power k. Okay, then we can write it as we have to separate x and lambda as good as possible. So we can write k by lambda, so we can write this as ln k minus ln lambda plus k minus 1 ln x minus k minus 1 ln lambda minus x by lambda whole to the power k. So this minus lambda and this plus lambda will cancel, so we'll have something like e to the power ln k plus k minus 1 ln x minus k ln lambda minus x to the power k by lambda to the power k. So here if we look carefully, then we'll be able to see that ax is x to the power k, this term, b lambda is minus 1 by lambda to the power k or 1 by lambda to the power k, this okay, and c lambda is minus k ln lambda and dx is ln k plus k minus 1 ln x. So the natural parameter is this thing, minus 1 by lambda to the power k. Okay, and one more thing, even if you are given plus or minus here, this really doesn't matter, but the form matters. Okay.
Yes.
Okay, so again I'm coming to the last question of today. I'm almost done. So is this density in its canonical form? What do you think? So I'll write down ax is x to the power k, b lambda is 1 by lambda to the power k minus, okay, c lambda is something. What was c lambda? C lambda, let's say minus k ln lambda, minus k ln lambda, and dx was what? Ln k plus k minus 1 ln x, ln k plus k minus 1 ln x. So how will you say whether it's in canonical form or not?
Yes, ma'am. This is canonical form.
No, it is not in canonical form because ax is x to the power k, and we don't know what k is. If k equal to 1, then yes, it is in canonical form, but if not, if k is not equal to 1, then ax is x to the power k, some other thing. So here they have not said what is k. Okay, and
Okay, okay. Yeah, it is given x is the nonsense parameters. If it is constant, then it is canonical form.
if ax equal to x, if this holds, then we can say it's in canonical form.
I'm talking about if k is the constant, then
Then also, if let's say here k is a constant only, I mean we are treating it as a nuisance parameter. We don't know what the value of k is. Let's say k is 2, then k is a constant,
yes.
but this is x square, ax equal to x square, not x. So
Okay,
then,
okay.
then
Understand now.
it's not in a canonical form. Okay. So
Similarly, we can do the normal distributions.
yes, and so the normal distribution also you can write it. You write the PDF of a normal distribution and then write it in exponential form, and then you see if this ay associated with b theta, if this is equal to y, then this is in canonical form. Like in Poiso, what we saw, if we go a little back, here you see ay is y, so this is in canonical form. Okay.
Okay.
Okay, so that was all about today's session. Please go back and if you can look at the lecture notes, if not the videos, and if you have any further doubt, you please post it in the discussion session. Okay, I'll try to answer.
Okay.
Any
Thank
specific
you.
doubt from the today's session, sir?
This is the last class, no? Last problem solving.
Yes, I believe so. Okay, so thank you for
Okay, okay.
joining and all the best for your exams. If you do have questions, please post it in the use the discussion forum. I'll try to address your doubts there. Okay, thank you for joining.